Hello, hello, hello. I'm here to help you solve these problems and how to resolve it. So let's take a look. It's a basic math question that we want to answer. Is you got a velocity, you have a particle at traveling velocity. And when I say velocity, it means speed. Speed is a rate. When you travel 60 miles per hour, that's a rate of how much distance you're covering in how much time. Okay? So we'll get back to that, but the equation is equal to velocity 1 plus t to the third power divided by 10 minus t squared divided by 20. And we want to evaluate how much distance do you cover from 0 to 2 seconds at that variable velocity. Okay, now, anyhow, this is velocity and this is time. Now, if you're traveling at 60 miles, right, per hour, and you travel for 2 hours, it turns out that the area of this rectangle is the distance covered. It's clear enough, right? You travel for 60 miles an hour for 2 hours, you've traveled 120 miles. Now, what happens when we have a velocity that changes with time? You get, going like this, you get faster, you get slower, you pick up speed. Now, if I ask you, how much distance have you covered? This is not so easy. So guess what? We use integral calculus. And how does integral calculus do it? Well, in the first thing you might think, well, look, this guy right here, from here, let me go. Use the highest spot here, see? Times this. Okay, right? Well, you can see that area is an overestimate. Or you might say, well, I could do this. What if I find one that's even smaller, like one to here, that touches the lowest point? Well, you can see the area of that rectangle would be underestimated. So we have a problem. It's kind of an estimate between those two problems. So somebody, and that was Leibniz, figured out, well, what if we put in so that this is really, in essence, the height is how far it goes up to hit the velocity function, the equation. And this width we'll create arbitrarily small, but equal across this. So we'll keep adding these rectangles. And so you have a bunch of little rectangles. It's true you have a little error here. You see how this corner overlapped? But if you keep cramming, the width of the rectangles get smaller, infinitesimally smaller, then you get less and less error, so that what they say in the limit is going to be perfectly the area under that varying curve. That's amazing. So we can actually, no matter whether velocity is changing or not over time, we'll know how much distance we can cover. Okay, let's do it. So in my case, in this problem, I should say, if you take a look at it, this I've changed. This guy was velocity, so I'm calling the y velocity, and I'm going to call time the x. Okay, so I've just substituted out different, only because we're most used to that. So what I really like to know is to find area. We use this guy here. That's called an integral. It looks like a big S, and S stands for summing. So what that S means is that we're going to add up all the areas of these little rectangles. And what does this mean? This equation here, why, that's the top of the rectangles at any given value of x, right? And this dx, believe it or not, is the infinitesimal width of the rectangle width. And that's how simple it is. Everybody freaks out about calculus. This is height. Top is the height. This is width. Okay, so height times width. Add up those areas between 0 and 2 seconds. Do it. That's how it's done. So if I take a look at it, the way you do the integrand, the shortcut of it, because you can do it rigorously, of course, in what they call in the limit. But let's just do the shortcut for now. In order to take the integral, what happens is that you look at the inside, and you have to add 1 to the exponent so that becomes 4. And that 4 then has to come down here as well and multiply times the 10. That's what it's called to integrate. And so too, then I'll subtract and I'll have x squared, you see? Well, that's going to become a 3. And then I pick the 3 under here, you see that? And I multiply that times 20. And finally, 1 is a constant. So the opposite of constant is just going to be x. This has to be evaluated now from the upper, what we call the upper limit, in this case 2. So we're evaluating from 0 to 2 of this equation. Okay, so that means first I'll take the area from 2 back to 0, and then I'll subtract any area from 0. There isn't any after 0. We're not calculating, so you'll see. So now I've got to plug in 2 first. So you take the 2 and plug it in. What do we have? We have 16. 2, because what does to the 4th power mean? That means 4 copies of x. That means 2 times 2 times 2 times 2 over 40. You agree? Oh, good. Now over here, 2 times 2 times 2 is 8. Right? And that's over 3 times 20, which would be 60. Because we added 1 to 2, that's 3, and then we brought the 3 down, and 3 times 20 is 60. And now, all you have to do is plug in 2 into the x, it's plus 2. And now I have to subtract the lower limit. In our case, it's really easy, because I'm going to reevaluate this whole thing, but now evaluate it as 0. So you can see what happens. I have 0 over 40. Yeah, that's 0. And I have 0 over 60. True. Well, that's 0. And then I plug in 0, and I got plus 0. So we don't have we have 0 to subtract. So my answer would be, by the way, this is going to be equal to distance. And this is going to be equal to distance. And so we just have to solve this problem, and let's simplify to begin with. I can see that 4 goes into 16 4 times, and 4 goes into, well, that even goes further, doesn't it? So 4 goes into 40. I mean, I'm just simplifying it. I don't need to, but it makes it easier to, well, I call it 2/5. Minus, well, let's see, 8. 8 goes, what? You can go 4, right? You won't know it. You can go 2. So that's 4. Oh, well, that's 4/20ths, right? So you can do 2/10. Oh, yeah, divide by 4. So you can type top and bottom by 4, right? And so what we have is 2. And then how many times the 4 go into 60, right? So we have 4 goes into 6 once. So we have like 15. Let's see, 15 times 4. 4 times 10 is 40, and 4 times 5 is 20, and that adds up to 60, plus 2. You see that? That's equal to distance. Now, it might be easy enough to get a common denominator so that I have everything over 15. It makes it easier. So I know if I multiply top and bottom by 3, I will have 6 over 15. Do you see this? And this is already got. And now, for 2, we can take the 2 over 1 and multiply top and bottom by 15. So what we have is 30. Over 15. I multiplied top and bottom. So now we have a common answer of 15. So let's see what we got. We have, this is 6, right? Remember, because we multiplied top and bottom by 3. Well, so we have 6 minus 2. Well, 6 minus 2, this is all over, going to be all over 15, right? So what we have is 6 minus 2, which is 4, plus 30, which is 34. So a fraction is nothing more than putting the top number in the box and dividing by the lower number. And if you go over here, you're going to see, oh, by the way, in our problem, this curve is this blue curve, as we saw, and then I showed you the graphing calculator. So what we're actually following is not, we're not calculating the area of this curve. I just drew it. We're finding the distance under this area by putting those, those rectangles in there. Like in here. See if I can do it. Yeah. And then I'll do it again. They're all evenly, they are the same width. And they stop when they hit the top of the, and that's what we're going to be adding together. and all the way over it. So that ends up giving us a perfect, not close. So, and then what I have here is 34 divided by 15. Yeah, I can do long division by hand, but I'm going to cheat. I'm going to say 34 divided by 15. And that equals, da da da, that equals 2.2 2.2666666 forever. What I'm telling you is that in 2 seconds, that's the distance you've traveled. I believe that was in meters. Okay? Okay, so that's where we're at. Next problem. Let's take a look at number 1 here. Let's say that you have a system, an algebraic system of equations, and you can tell by the power of the variable, the exponent is 1. And since it's only 1 for both x and y, we know that this is a line. And the other one is a line too. So if we take a look at what the graph of that looks like, let me go over there, and let's see if I can I just go over there like this? Yeah. So what you have here is, let's say, so this line is the blue line, okay, and this line is the black line, and we're going to learn something that's, let's see if the guy, yeah. And where they intersect, you can see that x is equal, well, if you want to call it x, is equal to 4, and y is equal to 8. That means that 4 and that 8, you can plug it, the 4 in the top equation with x, and then you use the 4, and you can use the same x and y value on the second equation, and they both come out equal 2. This is the only place in the universe where these two lines intersect, and that's called the solution of a system of equations. Let me show you an example of where that would come into play. Suppose we're talking about economics, and so I'm going to say that we're talking about the first quadrant. So this right here, let's look at the black one. This is demand, and if you think of the x-axis as some price, let's say price, and you think of this axis y as a demand for a product, then as the price goes up, the demand goes down. So that's the demand line. Now, a manufacturer is willing, as price goes up, to produce more. And there is where both the supply and demand meet. It's considered the optimal amount, the price you should sell it at, and the optimal amount you should build to meet that demand and supply. So let's see if we can find a solution. And the way it looks like where where it intersects here, you see, they're saying x is 8. So in that case, let's say you have a price of $8, and you're going to tell you to make, it could be for thousands, and then the other 4 for, well, I mean, you could consider 8 standing for 8K, meaning 8,000, and 4, let's say that you should produce like 4,000, for example. So then let's check that out. So let's see how we would solve that kind of problem. What we have here is we have 3/4 times x minus y equals 2. That's the one equation. And then we have this one here where it's 1/8 times x plus 1/4 times y equals 2. Now I'm going to use what's called clearing the denominator. I think it makes calculation easier. So I'm going to put parentheses around the first equation, and then the second equation, because I have an 8 under the denominator and a 4, I would like to multiply by something that only leaves a 1 under there. So if I distribute the 8, you see, there, that's 8. And if I distribute it over here, well, this ends up being 8 over 8, right? So, and then if I distribute over this, 8 here, 4 divided by 8 is 2. And to be fair, I have to multiply both sides. So there you have this, and because I did that, I got the wrong one. Here we go. So then that's why I have to multiply this side too to keep the equation balanced. Right? So there you have it. And now that's going to be 16. Now we're going to run the 4 through on the second equation, which is the first equation here. And the 4 will divide out with this 4, and the 4 times the minus y, but again I have to multiply this side times 5. 2 times 4 is 8. And now as I run it through, the 4's divide out, so all I'm left with is 3x minus 4y. Well, that's easier to deal with. Now we're going to use what's called linear program to come up with a solution. Linear program is a process of elimination and pivot. So the idea is to eliminate one variable so that now we can solve for the other variable and then use that to get the final answer, the following answer, and then the next answer. So what I do is, if you notice that there's a coefficient in front of here, 1. We don't put it there because we know 1 times x is x, but that 1 is this 1 right here. Yeah. And then this is, notice that I'm leaving the variables out. So I'm just putting the coefficients, and then the equals is on this right side. And the other one too, I leave, you see, I use just the coefficients. You have the 3 and a -4 and the 8, yeah? So now the linear programming, the actual thing that programs are written to solve linear equations where they eat, where the elite meet to eat, is the intersection, is the only place with that same value of x and y are solution for both equations. So what I'm going to do is I'm going to take the first row and I multiply it by -3. And the reason I chose -3, because if I add it to this 3, it would be 0. You see that? And now, the other thing is this. As I come through, I put these red numbers up here because -3 times 2 is -6 and -3 times 16 is -48. But I'm not actually going to change the first row. I'm going to use those numbers and add it to my second row. By doing that, I end up forcing this to be a 0. Right? And then one could think of it, maybe it'd be easier. Let me solve it this way instead of, let me just make a small make a change. Hold on one second here. Alright, so now I'd like to drive this -10 to 1, because keep in mind that this column represents the x and this column represents the y. So I can simply take this last number and not change anything. It's like multiplying, like I did here, by 4 on one side and 4 on the other. You haven't changed anything because you did it equally on both sides. So what I can do here, I say, okay, I can multiply this place and then add it to itself. So I'm going to multiply this times 1/10. Right? It's like the reverse of clearing out the fraction. Well, 1/10 times 0 is 0, but 1/10, actually let's do -1/10. So 10 divided by 10, because that'd be 1 times -10 divided by -10. Why, that's +1. And -10 divided into minus is 4. So we automatically read off the answer. Look at that. So what I end up having is I have 1, 2, 16, and then I have 0, and then I have 1, and then I have -40 divided by, and I have 4. Do you see? Now, keeping in mind that this is the x column and y column, we'll put it back into algebraic form, so that this first line would be 1 times x is x, plus 2 times y, you see that, is equal to 16. And this one, we have eliminated one variable, but 0 times x is x, and 1 times y is y. So we have y equals 4. Dun, dun, dun. That's a beautiful, that is the optimal number of units you should make at the price. Now, what price should you sell it at? Well, then all I have to do is take this special, I'll put an asterisk here. I'll take this value of 4, just got a little carried away here. I'll put it back in. I take this value of 4, still, okay, this value of 4, and that's what this y star is. This is a y star. The star, the asterisk, meaning it's the optimal value of y. Now, to find the optimal value of x, I'm going to take this guy, this 4, which is value of y, and stuff it into this y. And now I'll be able to solve for x. So I have x plus 2y, right? X plus 2y. Well, but we'll replace the y with 4, and that equals 16. Well, that's x plus 8. What did I put 8 here for? Isn't that weird how the brain works? That's 16. Okay, so I have x plus 8. And there it is, x plus 8 equals 16. So now I have my ultimate price, optimal price that I should sell it at. And I have x star asterisk, it's like x raised, x asterisk, the optimal point is equal to, well, I'm subtract 8 from both sides, equal to 8. So the optimal point in this system equations is going to be an x value of 8, and the y value is going to be 4. And as a reminder, let's look back at the graph. Right? And there we have it. Look at that. Let's move it right up to the point. There it is. Look at that. Dun, dun, dun. All right. Let me know if you have any questions.